Next, we're going to discuss the properties of power functions, starting with the whole number powers. Now, we've already talked about the properties of the power functions, but now knowing what we do about the transformations of graphs, we can state these properties in a much simpler, much easier to remember way. We'll talk about the even powers first and the odd powers second. The basic form of an even power function is f of x equals x to the p, where p is even. And our example here shows f of x equals x squared. Larger powers of p will be less rounded near 0 and steeper far from 0. The domain of these even power functions is all real numbers, and their range is 0 to infinity, the positive real numbers and 0. These functions don't have inverses per se. They're not 1-to-1, but they are 2-to-1. So they don't quite have inverses, but if we restrict the domain to positive numbers, then we can take the pth root to be an inverse. And if we restrict the domain to negative numbers, we can take the negative pth root to be an inverse. So we don't have an inverse for the entire function, but we can split up the domain in such a way that we can take an inverse. Part of the reason that we need to make that move in splitting up the domain is that this is an even function, which means that it's symmetric across the y-axis. Now notice, even power, even function, that naming is not a coincidence. We call it an even function, in fact, because it behaves nicely in this way, the way that even power functions behave nicely. These functions still have no asymptotes, and if we go to graph 1, we'll typically use the points -1, 1, 0, 0, and +1, 1 as our key points to transform. The odd power functions are fairly similar, but the oddness of the exponent changes the properties slightly. The basic form is still f of x is x to the p, but now, of course, the power is odd. Our example function here is f of x equals x to the third. Larger odd powers of p, again, will be flatter near x equals 0 and steeper when x is far from 0. Like the even power functions, the domain of an odd power function is all real numbers. Unlike the even power functions, their range is also all real numbers. Odd power functions are 1-to-1, so they have a true inverse, which is the pth root. The even power functions were even, the odd power functions are odd. And again, that naming is not a coincidence. We call them odd because they're nice in the way that odd power functions are. Odd power functions, positive powers still have no asymptotes. And when we go to graph 1, we'll use the key points -1, -1, 0, 0, and 1, 1. We have a couple of notes to make about power functions before we go on. First, about the graphs, as we mentioned, if the power is larger, the graph becomes flatter near 0 and steeper when it's far from 0. So, as we get very, very large powers, we end up looking more like we have square corners than like we have smooth curves. The next thing to note is that because we can complete the square, every quadratic function can be seen as a power function. This isn't true of all polynomials. We can't, for example, in general, complete the cube in the same way that we could complete the square. The last thing to note is that, technically speaking, a linear function belongs to the family of power functions with exponent 1. It has all of the properties that we've discussed so far of an odd power function. But it doesn't do that swoopy S-shaped curve thing that most of the odd power functions do, so we usually don't think of it as a member of the family, even though it technically is.